On this worksheet, we're going to practice completing nuclear reactions. So each one of these is a nuclear reaction that's missing some component being represented by X, and our job is to figure out what is being represented by X. Nuclear reactions are not balanced by the particle, by the atom. They are instead balanced by mass number and also by atomic number. So in order to balance these equations, we want to make sure that the mass number is the same on the left-hand side as it is on the right-hand side. And on our left-hand side, we can see that we have a total mass of 27. 26 plus 1 is 27. So that means on the right-hand side, we need to have a total mass of 27 as well. And then we're going to do the same thing for our atomic number. The atomic number is represented in the lower left-hand subscript, and that is, in this case, it's 12 plus 1 is 13, so we've got a mass number, or an atomic number of 13. We need the same on the right-hand side. For whatever reason, this alpha particle here is missing its little symbols. Alpha particles have a mass number of 4 and an atomic number of 2. We really need to know that to be able to answer this question. So we know that whatever is being represented by X, it needs to have a mass number of 23, because 23 plus 4 gives us 27, and it needs to have an atomic number of 11 because 11 plus 2 gives us 13. To figure out what this element actually is, we need to go to the periodic table and we need to find element number 11. So I've got a periodic table over here for reference, and element number 11 is sodium. We're looking at the atomic number. We're not looking at the mass number for sodium, which is 22.99. We're looking at the atomic number, the number of protons. That's all there is to these problems. They're pretty simple. Let's look at our next one. On the left-hand side, our total mass is 59 plus 2, which is 61. Which means over here on the right side, our mass needs to be 61 as well. And that tells us that this particle X, it must have a mass of 1. 60 plus 1 gives us 61. For our atomic numbers, on the left-hand side, we have a total of 28, which means over here we need to have 28 as well. And what element would that be? So this is element number 1, and that is hydrogen. There. This one looks like it's going to be a little bit trickier because it has a 3x on here. So let's add up what do we have. On the left-hand side, we have a total mass of 236 and a total atomic number of 92. And on the right-hand side, that means that we need to have a total mass of 236. I'm actually going to use my calculator for this just to make sure that I don't make any subtraction errors. So to figure out what's being represented over here, the first thing that I'm going to do is just solve for the missing mass. I'm not going to think yet about the fact that it's 3x. I just want to figure out what the missing mass is going to be. 236 minus 94 minus 139 is 3, and that 3 is being distributed over 3 particles. So I want to divide by 3. That means each one of these X particles has a mass of 1. For our atomic number, I'm going to again begin by figuring out what my missing atomic number is. I'm going to take 92, subtract 36 and 56, which is 0. So divide that by 0, or divide that by 3. That's just a 0. So we need to figure out what this is. This is not an atom because atoms have to have at least one proton in them. So this is not an atom. This is a particle. A particle that has a mass number of 1 but no protons in it at all. That's a neutron. So that's represented by this notation right here. Let's take a look at our next example. On the left-hand side, we have a total mass of 57. So that means on our right-hand side, we need to have a mass of 57 as well. X needs to have a mass of 56. In terms of atomic number, we have a total atomic number of 26, which we need on this right-hand side as well. We have 0 atomic number for our neutron, so that means that this needs to have an atomic number of 26. We got to figure out what this element is. We're going to look for element 26 on the periodic table. Element 26 is iron, Fe. Looking at our next example, our mass number is 20 on the left-hand side, and so that means on the right-hand side, our X needs to have a mass number of 0. 20 plus 0 is going to give us 20. Our left-hand side has an atomic number of 8. The right-hand side has an atomic number of 9, which means we need a negative atomic number for this guy. 9 minus 1 is going to give us 8. This is not an atom because you can't have negative protons in an atom. This is a particle, and this is an electron. It's also referred to as a beta particle, so you could also see it written like that. And while we're on track of other ways that we can write these, up here, the hydrogen atom, this could also be written as just a proton. Here's our next example. This one, we have a mass number of 135 on the left and also already present on the right, which means X has no mass. We have an atomic number of 53 on the left and 54 on the right, so that means that on the right-hand side, we need to have an atomic number of -1. That's going to be an electron or a beta particle, whichever notation you would like to use. For this one, our mass number, we have 40 on the left. We need to have 40 on the right. X needs to have a mass number of 40. We have an atomic number of 19 on the left-hand side and an atomic number of -1 on the right-hand side. So that means we need to have, X needs to have an atomic number of 20. 20 minus 1 is going to give us 19. Now we need to figure out what element has an atomic number of 20. That is calcium. We've got 2 more to go. On the left-hand side, atomic or mass number of 60. So that means that this X must have a mass number of 4. 59 plus 1 is 60. 56 plus 4 is 60. Atomic number 27 on the left-hand side. So we need an atomic number of 2 for our X. 27 plus 0 and 25 plus 2. This is an atomic number of 2. This is helium. I don't know why all of a sudden my periodic table has changed colors. That's okay. Atomic number of 2 is helium. This is also in nuclear reactions sometimes written as an alpha particle, so you could write it either way. And for our last example, on the left-hand side, we have a mass number of 236. On the right-hand side, we need 236. We currently can see a mass number of 99 and a mass number of 135, which means that we have a remaining mass of 2. We can see that that's being accounted for in 2 particles. So each one of these particles has a mass number of 1. For our atomic number, we have 92. And over on the right-hand side, we can see an atomic number of 40, and we can see an atomic number of 52, which is 0. So that means we have no atomic number in these particles. This is not an atom. This is a neutron.